Hello, this is Mason Haggerty with question 53 from Chapter 2 of the Fundamentals of Heat and Mass Transfer, 8th edition by Bergen. In this question, we have a steady-state temperature distribution in a composite wall of 3 different materials, each of constant thermal conductivity. There's section A with heat flux 2, there's section B with heat flux 3, and section C with heat flux 4. So part A asks us to comment on the relative magnitudes of thermal flux 2, 3, and then of 3 and 4. So to begin, we want to list our assumptions, which all come directly from the question. We know that it's steady state, we know that it's 1D conduction, and we know that it has constant properties. So to get into A, the first ones we want to look at are heat flux 2 and 3. We can see from the temperature distribution graph that the temperature distribution is a linear distribution across sections A and B. Because of this, we know that there is no heat generation within those 2 sections. Because of this, we can know that the heat flux through 2 and 3 are the same. The heat leaving B is entering A, and because there is no heat generation, that must mean that the amount of heat leaving B is entering A. However, when we look at sections heat flux 3 and heat flux 4, we know that they are different. Because heat flux 4 has a curved temperature distribution, we know that heat generation is occurring. Because again, this is in a plane wall, so in a plane wall with 1D conduction, it should either be linear or there is heat generation. Because of that, we know that it is not there is not a constant flux through the entirety of C, and therefore we know that by looking at the parabolic curve in section C, we can see that as x increases, dt dx decreases. That means that over section C, as we move further in the x direction, the heat flux will decrease. Because of this, we can say that Q3 is relatively larger than Q4. Next, part B, we are looking at the relative magnitudes of Ka and Kb and of Kb and Kc. So let's begin with section A and B. In these sections, we know that the temperature distribution is linear, and we now know that they have the same heat flux. So let's look at Fourier's law, where we know that the heat flux is equal to negative K dt dx. Because of this, and knowing that they have constant properties, we can say that because A has the larger slope, that must mean that K is smaller than in section B. Because again, we can set them equal to each other, where negative Ka dt dx is equal to negative Kb dt dx. And from that, with knowing that the dt dx is larger in A, K must be smaller. Looking at sections B and C is a little bit more complicated, but not significantly so. We know from conservation of energy that Q3b and Q3c, meaning the heat flux on either side of line 3, must be the same. However, looking at the dt dx, we can see that on the B side, dt dx is significantly less than dt dx of the C side of, again, line 3. From this, we can once again know that Kc is less than Kb, to again make Fourier's law true, where Q is equal to negative K dt dx. This leaves us with our final answer that Ka is less than Kb, and Kb is greater than Kc. Finally, part C. Sketch the heat flux as a function of x. So first, looking at sections A and B with their linear temperature distributions, we know that the heat flux will be proportional to the derivative of those heat temperature distributions. From this, we can see that it will be a constant for both of those sections. We also know from earlier that the conservation of energy requires that the heat flux through all of sections A and B are equivalent. This leaves us with a flat line parallel to the x-axis through the entirety of sections A and B. So for section C, we can see that instead of a linear line, the temperature distribution is parabolic. From this, we can know that the heat flux, which again is proportional to the derivative, will be defined by 2x. Looking at this, we can also see that the heat flux will be approaching 0 as we're approaching line 4. So from this, we can see that in the graph of heat fluxes, In sections A and B, there will be a flat horizontal line, while in section C, a linear slope will move the heat flux towards 0.